So without further ado, we will start with our first lecture, Amir. Amir Bousani is the co-founder and CEO of Argo Robotics. He's going to talk about visual perception. Specifically, I worked with Amir at Intel. It was a great experience. He's a great guy and very smart, so we're going to have a blast. Please come.
I'm really happy I came just to hear Amit say all that about me. So I'm done. Great. So while we set up the presentation, I'm really excited about this meetup. And I just came from a conference in Santa Clara, the Silicon Valley. And there are more experts in robotics here than I think what I saw here. So it shows a lot about the Israeli community for robotics and where we are. And one more thing, the statistics that Amit showed, it shows a real change in the robotics world. So if you looked at robotics a few years ago, it was mostly electrical and mechanical engineers, and the switch to software and algorithms, of course, no offense, is an important change. So the challenge in robotics is switching to software, and that's a big part of what I'm going to talk about. So today I'll give you just a short lecture explaining a little bit about visual perception in general, a bit more about what we do in the context, in Argo Robotics, what we do in the context of visual perception, and more specific to the domain of mobile machine automation. Robotics, of course, I'll use the word robotics, but it's more general than that. The need for a machine to move from one point to another and to do that intelligently, even in complex environments. So when we talk about mobile robots, there are many different use cases. These are just a few of them. And if you talk to the average man on the street about robotics today, he'll talk about your Roomba. We all understand that that's just the tip of the iceberg. Many use cases for mobile robotics. I'll focus mostly on wheeled robotics, ones driving from one point to another. And all of them share the same needs. So these machines need to be able to move around from one point to another, and to do that even in complex environments. To do that, they need to be smart enough. So that's what visual perception is about, the ability to understand, to see the environment, to see and to understand what we see to the level that a machine can be intelligent enough to be truly autonomous and to be able to move from one point to another. So a very basic need in robotics, but one of the bigger challenges. When we look practically about the need for a mobile machine, let's take that as an example. In order to be able to move around, it needs to really understand what it sees. It needs to detect different types of obstacles and understand the space around it. It needs to understand how to behave in different environments. So looking at that, we have defined 4 main areas of needs for visual perception. It's actually the combination of all that creates a machine that is intelligent and has true visual perception. So first, it needs to understand where it is, the exact position of the machine. It has to be accurate, it has to be robust. GPS, for example, is usually not enough. You want centimeters level of accuracy in order to really perform the task. On top of that, it needs to understand its surrounding. So first, at the geometrical level, just to understand where are the obstacles, what's the distance of the obstacles, the height of the obstacles, and how to move around between them to get to the destination. At the highest level, the machine needs to know a little bit about the environment in order to know how to behave correctly, right? So this is a classic example. If there's a person in front of the robot, the machine needs to behave differently, to take some safety distance, and to expect how it will behave. These are really the fundamental needs when it comes to visual perception. Now, it all sounds easy, but this is considered the biggest challenge in robotics today, one among many other challenges that we believe that will come. And for me, looking at what's happening in autonomous vehicles, that's where I want to see robotics. I've been in a lecture by Waymo, seeing the huge data sets that they're using and the amazing perception their virtual driver has. That's what we want to have in robotics. It's a huge challenge. And more than that, for most robotic companies, this is what can block them from deployment. So there's no real off-the-shelf solution. I know there are many attempts. You'll see a lot of work from open source to different types of sensors. Sensors are becoming available, but a machine with the understanding and the ability to analyze the sensors is not really available. So everyone that tried to make a robot to be able to move around in complex environment knows that this will require a lot of work. It requires unique expertise that is not widely available. There's a need to know geometrical computer vision, deep learning, sensor fusion, complex tasks, and there's a need for long development. So practically, it takes many years to develop such a system. Many robotic companies, and I meet a lot of them, say, okay, we'll deploy a robot next year. No, it usually doesn't happen. Just one example, iRobot. I think iRobot today have the best visual perception solution available at masses. They're selling millions of units. They've acquired the company, Evolution Robotics. They've been working on that for more than 15 years, spending probably more than $100 million on that. And at the end of the day, today, their perception is around localization, right? From the 4 tiers I showed, localization, a little bit about obstacle detection, no real semantic understanding or behavior. It's still far away. So with that challenge, that's what drove us to found Argo. And our goal was to solve that problem with the vision that once a solution like that is available, more robotic companies can deploy products, get faster to the market, and focus on their specific application. So we focus on how to move from one point to another, while the robot company can focus on building their specific application in a variety of use cases. So in Argo, our focus is on what we call human level perception for robotics. When I say human level, it's mostly the ability to move next to humans. So you need to have same level of understanding. The idea is to focus on environments that are complex. So robotics are deployed pretty well today in static structured environments like manufacturing lines. Anyone that's seen Amazon Robotics, this is a caged environment for robotics. We have good deployment of robotics there. But our goal is to enable mass deployment of robotics in challenging outdoor environments, uneven surfaces, next to obstacles, next to other moving machines like forklifts or other robots in the real world. For that, our focus was on a solution that can work hand in hand with the machine manufacturer, that can allow the machine manufacturer to design the entire machine, to integrate the components that are needed, the different types of sensors that are needed for that, and to have a solution that provides the real-time information on the edge, because still today we cannot assume constant connectivity, so cloud-based solutions are not enough for the real-time part. Right? The system wouldn't be safe if it will count on the cloud, but still leverage cloud capabilities whenever possible. The solution that we've decided to implement was based on many years, more than 10 years of experience on looking at solutions that failed and figuring out what's the right way to solve that problem. We've looked at computer vision-based solution because we believe that only vision, computer vision and camera-based perception can really provide all that information while using all the advanced sensors that are available. So an advanced sensor fusion mechanism that can use different types of sensors, the more the better. The limit is just the price point that is fitting the machine. And using as much sensors as possible in order to add more and more layers of redundancy to keep a flawless operation. We've designed a solution to work on a single camera as a minimum, because we believe that camera is going to be on every type of robot. So the minimum structure should include a camera, some low-cost sensors like gyro, accelerometer, magnetometer, wheel encoders, and compute at the cost that can fit a robot. So aiming for, in autonomous vehicles, you can fill the trunk of the car with GPUs. In most robotic applications, that's not acceptable. So you need the compute at the cost that can fit robotic applications. In terms of the information, we are looking at layers, what we call layers of perception. So providing different layers of information that will include all the data that the robot needs. It has localization, 6 degrees of freedom position. We'll talk a bit more about that. The ability to map the environment and to generate different types of maps. Sometimes 3D maps are needed, sometimes 2D maps. There's value in simplifying the data sometimes, coverage maps and similar, obstacle detection and geometrical understanding of space, recognition of specific objects and being able to label specific objects. And by the way, on that point, for robotics, the needs are pretty different than what you see in other domains. So I've been talking to hundreds of robotic companies. The need to distinguish between a cat and a dog is nice to have, but it's not crucial usually for robotics. The focus should be on where it makes a big difference, which is usually human detection or environment classification, detecting if you're driving on the road or on the sidewalk. Right? That makes a difference. And at the highest level, capabilities around scene understanding, things like detecting moving objects, right? That always impacts the path planning, and detecting movable objects, right? Being able to detect objects that are likely to move even if they're static now. When I cross the street and I see a parking car, that's a movable object, so I'll take some safety distance or just make sure there's no driver. That level of understanding is needed for robotics. We're not there yet. There's a lot to develop, but that's certainly the goal. Consider a few examples of the type of hardware that we've aimed the system for. We believe that this can be enough. So small camera, small compute, ARM level SoC, that should be enough for basic perception, and more sensors will improve that. So a bit about the challenges and how we implemented the technology. One of the biggest challenges in robotics is the endless number of use cases and applications. Almost every robotic company has a different machine, the structure is different, and the use case is different. So there are a huge variety of applications. We have focused on 5 of the main ones, and we're already working with companies in this domain with the assumption that once enough of that is covered, other applications are close enough. And you can see the variety from outdoor machinery, agriculture machines, all the way to manufacturing line automation, and even man-driven applications such as forklifts. Very different machines, very different use cases, pretty similar perception. The need is pretty similar. But we're a technical forum, so I let myself dive a little bit deeper into the challenges of the actual implementation. These are the 4 main areas needed for the development. The first part, localization. Many of you probably know the classic approach of visual SLAM. Farmers are using usually visual SLAM-based approach. For those who don't know, the main concept is pretty simple. You take one picture, the robot moves a little bit, you take another picture, you find reference points in the 2 pictures, and then if you collect enough such points, you can solve the equations of both the 3D position of each one of the points, plus the pose, the X, Y, Z, and the angle of the camera for each one of the frames. It's a well-known approach. The main problem with that approach is that within every such 2 consecutive frames, there's a small amount of error that is accumulated. It's not a lot at the beginning, but once you accumulate that over time, the error becomes big. The best algorithms claim about 1% of error, sometimes claim 0.5%. But when you're looking at a machine driving hundreds or kilometers within a day, that number becomes way more than what the system can cope. So for that, we've decided to take a completely different approach. And we have tried to imitate the way human beings are seeing their environments and to memorize structures in the environment. We call it a learning vision system. And the main value of doing that is that whenever we see something we've seen before, 2 minutes? Great. No, not dead yet, so I still have 2 minutes. But we got to the fun part. The main advantage is that it doesn't accumulate error. I want to show you just a few examples since I have only 2 minutes, so that's all right. Because the calculation is not, it doesn't integrate the data from the previous one. It's all based on global data. It's kind of like GPS, right? In each sample, you get the exact pose, and it doesn't depend on your previous pose. I want to show you an example of the kind of challenges and how it looks in the real world. So this is an example taken by one of our customers operating a logistics platform within one of the biggest convention centers in the US. You can see some of the pictures as we see them from the robot. Extremely dynamic, a lot of people moving around, a lot of carts, right? These are the environments where you want robotics to operate. Today, current technologies are just not good enough for that. Laser scanners-based navigation or even visual SLAM will not be able to solve these environments. Now it should work, yeah. Okay, so it looks good. It works. You can see how it works. No error at all. You see perfect behavior. Who's of you who are interested, and I can send a link later, and you'll have to believe me that this technology works. I do want to show you. Let's see if that video works. Cannot play video. I think we'll skip to the next one. This one works. Partially. We have the 5 minutes for questions, so I think we can stop at this point.
Thank you.
Yeah. Just one last slide. We won't get to talk about it, but some of the challenges around detection of humans in robotics. It's very different than human detection in other cases when looking from the point of view of the robot, and when in many cases what you're detecting is not really a full human body, but the part that is seen by the robot. That's an area of research in which we've done a lot of work. You can see some of the challenges, right? That has to be detected as a person, though all you see is really a hand and part of the body. Any questions? Go ahead.
The question is, if the viewpoint of the robot, or if it will learn how it will do it. So which the person in robotics will be a big problem.
So I'll repeat the question. The question was, what if your point of view will change? If you're implemented on different robots, each one sees the environment from a different angle. So there is some perspective that is important. So if the point of view is very different, looking from 10 centimeters and looking from 10 meters, it will look very different at the short range. Most of the things will look similar. So if you can see the same, this is a perfect example. So if there's this drawing on the wall that can be seen from different points and different perspectives, that will work. If the perspective is so much different, then at some point we will probably want to learn the environment by multiple machines at different heights. Another question there?
Classify objects according to the characters, right? It's talk about objects that might be movable. They may move or not. Do you do some kind of prediction where this object might move? For example, if you have a car, it obviously, if it moves, it would move forward or back, but it cannot move sideways, right? A person running, with one leg forward or one leg backwards, suddenly go forward.
An excellent question, so I'll repeat that. He's asking, more than detecting movable objects, can you detect the vector of movement and to predict the vector of movement even if the machine is not moving? So that's a great example. When you think about the use cases where we are walking alongside another machine, we take some assumptions about the movement of the machine, right? We'll move next to it on the same vector, but we will not cross it past. So yes, that's certainly one of the needs in this domain. It's not that simple. There are simple cases that we can solve. For example, when there are wheels and we can detect the direction of the wheels, not all of them are solvable. And there is going to be an important question about safety. So can you take different safety distance from a machine if you can predict something about a movement? We're doing part of that. There's still a lot of work to be done. And I think these are the kind of environment or kind of challenges where you will see more and more innovation coming up in the next few years.
Next question.
So one from that side, yeah.
Many different problems, right? Makes sense. So what is your approach of adjusting your solution to the new sensor of each robot?
So the question was, if you're applying your technology on many different robots and each robot has different sensors, what's your approach to solving that? So today our approach is that we are dictating the basic sensors that we need. So we're telling the machine manufacturers what sensors to integrate for the important one. We have a list of supported sensors, including a specific camera module that we've chosen, specific IMU, and specific other sensors. I assume that as we grow, we will support more and more of these, so they'll support more of the standard sensors. But today we do not support just any camera you have with any type of machine. And there's value in selecting the right sensors, global shutter images, the right field of view of the camera, the right IMU that has the noise characteristics that we know how to solve. There's value in selecting these components. Okay.
Sorry. Thank you, Amir. You can grab him afterwards for more questions. So